Welcome to this online lecture on cryogenic hydrogen application or cryogenic hydrogen technology. So, today we are going to talk about the hydrogen properties. In the previous class we have seen that the hydrogen properties are very important, and we will try to learn some of the fluid properties or the properties of this gaseous or hydrogen. And if we have to liquefy this hydrogen, we will start from gaseous hydrogen, and then finally, we will come to liquid, or sometime to densify we have to go to the solid phase. So, we will now try to look into the different phases of the hydrogen, and along with that we will also try to find out what are the different physical properties that we often come across while compressing it or expanding gaseous hydrogen and so on. So, let us now look into it. This is the concept that we will cover in this lecture today, and later on we will look into the different production means. These are the keywords: normal boiling point, triple point, critical point, phase diagram. I mean these all three parameters are basically related to the phase diagram of the hydrogen. And then we have TS diagram. We will also try to learn about the TS diagram in this lecture. So, this is what is called the phase diagram. In this phase diagram, it is a relation between the pressure and the temperature, and we know that this hydrogen exists in different forms, be it solid, liquid, gas and vapor. So, and there are different regions separated by some lines. We will see what are those lines. So, here comes the critical point, and this is the triple point. So, now let us look into the different regions. So, it is called, in this part it will be solid, and here comes the liquid between the triple point and the critical point. This is where the vapor phase will be existing. So, between the critical point, if it is below the critical point pressure and if it is below the critical point temperature, then we have this is what is critical point, and from here if we vertically drop down, this is the critical point temperature, and if we move on this side, it is the critical point pressure. Similarly, we have the triple point temperature and the triple point pressure. So, if we move from this end to this end, if we move from say the liquid part to the vapor region, we say that the liquid is vaporizing, and from vapor to liquid we say that it is condensing. Similarly, from here to here, when we move from the solid will melt, and solid will liquefy or it melts to the liquid, and from here it the liquid solidifies to liquid will be moving to the solid region. So, when it moves from the solid to directly the vapor, we call it sublimation, and when we move from this direction from vapor to the solid part, we call it deposition. So, these are the different activities or phenomena which occurs, and we are mostly familiar with this. If not, it will be a kind of recapitulation for you. So, as cryogenic engineer, we are concerned about this region between the triple point and the critical point. In this region, it will be existing as the liquid. So, we have identified vapor, liquid and the solid. So, where comes this gas? Is it different from gas and vapor? Yeah, in terms of strictly speaking, this gas and vapor are different. Vapor is only when it is below the critical point temperature and pressure, and here this is the vapor, but when it is above the critical point, then it exists in the form of gas. So, in gaseous form, most of the time you will find hydrogen to exist. So, if hydrogen has been given to some quantity at room temperature, we call it as gaseous phase. How do we know its state? We will see later on that it is two physical parameters, two parameters will be necessary. So, that is given by the Gibbs phase rule C minus P plus 2. Those are the parameters that will determine the number of phases present in that the number of independent variables that we need to specify or know the state of that point. So, here is the C is the number of components. Say here this is a single component hydrogen, and the number of phases, if it is a single phase, then we have this is 1, this is 1 and this is 2. So, for gaseous hydrogen, it is a pure component single phase, we need at least two parameters to identify, say maybe it is pressure and temperature. So, whenever we are talking about say hydrogen or any gas, any cryogen, and we have to specify, if it is in single phase and single component, we need to specify two state points. So, now let us look into the phase diagram of hydrogen in reality. So now that was a generalized diagram. Here comes the actual diagram of hydrogen phase diagram. This is the critical point. This is what is the critical point. So, corresponding value we will check later. This is the triple point where all these three phases will coexist, vapor, liquid and the solid. So, here this is the solid region, and here this is liquid, and on this side you have the vapor. Now, above and this side you have the supercritical zone, we have the gaseous zone, and here comes the compressed liquid part, and here it is solid. And now, this is from this chart we can find out the normal boiling point. So, what is mean is that at atmospheric pressure, what is the boiling point? It may be difficult to figure it out from this diagram. We will try to locate it in another diagram later on. So, it is the normal boiling point is 20.3. Then comes the triple point temperature, critical point temperature, that comes from here. So, if we drop a vertical line from here, we see that this is 33.2 Kelvin. Next is the critical point pressure. So, if we move from this end to this end, it is nearly 13 bar or nearly 1.3 MPa. So, it won't be, again I tell you that it is not very difficult, it is difficult to figure it out from this graph, but the triple point temperature and the triple point pressure is 13.9. This 13.9 can be easily obtained from here, but the corresponding pressure it is difficult to understand from this graph. So, these are the some parameters or numbers we have to remember, particularly for the hydrogen. Now, from this diagram you see here this pressure has been plotted in the logarithmic graph, and from here it will be easier to figure out all these numbers once again. This is the critical point and the corresponding temperature would be on this side and critical point pressure would be on this side. Similarly, this is the triple point, and we know that the boiling point, normal boiling point would be corresponding to 1 atmospheric pressure, that is nearly 1 bar, and from here if we drop a vertical line it is 20.3. So, we have normal boiling point. Once again this T c is the critical point temperature, critical point pressure, and this is the triple point temperature. Now, it is not that difficult to figure it out that this is 13.9, and the corresponding pressure on this side is subatmospheric, it is 7.2 kPa. So, we will try to remember these numbers, so that we can easily distinguish if we state the temperature and pressure for a gaseous hydrogen or vapor hydrogen. If it is in vapor state or in the gaseous state or in the liquid phase, we can make out if someone tells about its temperature and pressure, and sometime both of it. Okay. And we will also try to find out this region is basically what we have said, that it is solid hydrogen, and a solid plus liquid mixture is that is what is called slush hydrogen. We will also try to look into that later on when during appropriate time. So, that is about this phase diagram, that is in the pressure and temperature relation for hydrogen. Now comes this TS diagram. This temperature entropy diagram will often be necessary, because if we want to compress hydrogen, if we want to expand the hydrogen, and we need to know what is the initial enthalpy, what is the final enthalpy, whether it is expanded isentropically, whether it is expanded isenthalpically. So, all this information will be obtained from this kind of graph or the TS chart. We will refer to this kind of TS chart. So, now let us try to identify some of the regions. This part is the critical point. So, first of all we need to locate this liquid vapor dome. This is what is called the liquid vapor dome, and here comes the CP critical point. This point is again important. This is the triple point. Already we have learned it in the phase diagram. This critical point temperature and pressure, we have already learned about this critical point temperature. We have also learned about this critical point triple point temperature for this hydrogen. So, now corresponding to this we have the entropy values also. So, this is where you have the solid and completely solid. This region is solid plus liquid. This is liquid and vapor. Inside this dome we have the liquid plus vapor, and it can exist in the liquid form only up to this region. Okay. This is, we call it as saturated vapor. This is saturated vapor. This is on this side we have the complete saturation, I mean not at the triple point. On this side, if we draw a line like this, this will be the saturated liquid. On this side we have the saturated vapor. So, there are what is called isothermal lines. So, these are these straight lines are the isothermal lines. Then isentropic lines are on this side, these vertical lines are the isenthalpic lines. So, these are the isenthalpic lines, these are the isotherms, and we have moreover other lines which have not shown here. So, let us first remove it, saturated vapor. Okay. So, let us try to draw some isotherms, sorry, isobars. The isobars are the constant pressure lines. So, it would be something like this. These are called isobars or isobaric line. So, this will now come like this, this will come like this from here. So, if it is 1 atmospheric pressure, corresponding to that line will be your 20.3 Kelvin. So, that is the normal boiling point. So, if we are somewhere here near room temperature, that is 300 K, if we assume, or roughly speaking it is 27 degrees centigrade and 1 atmospheric pressure. So, if you have to liquefy this gaseous hydrogen from this temperature and this pressure, you have to come down to 20.3 Kelvin, or at this point it will be the saturated vapor. From there, at this point it will be the saturated liquid. So, if you are at a higher pressure, as we move from this point to this point, it will be like this, and till this point you can have it in the liquid form. This pressure is nearly 13 bar or 1.3 MPa, as we have noticed in the earlier slide. So, there are now different kind of other lines. Now, we will try to locate the we have identified the isotherms, and then we have identified the isobaric lines. Now, we will try to locate the isenthalpic lines on this diagram. So, the isenthalpic lines will look like it's, let us try to draw. You will find that there are this kind of lines which are called the isenthalpic lines, okay, and some of them will come inside the liquid vapor dome. So, these are isenthalpic lines. So, on this line the enthalpy will remain constant. The enthalpy remains constant along this line. So, we have also seen the what is called isobars. So, these are the isobars, these are the isobaric line, and say if we have to move from this higher pressure to a lower pressure following an isenthalpic process. So, you will find that there is a drop in temperature by this amount of So, this is higher enthalpy, this is higher pressure, this is a low pressure. So, when we expand the gas from high pressure to low pressure and in an isenthalpic process, or sometime we call it free expansion, there would be a temperature drop according to this. So, this is a typical TS diagram, and from here if we move say from this kind of pressure, if we move from this pressure to following an isenthalpic process, we will come inside this liquid vapor dome. So, as I have said that if we want to come from this, we have to have some refrigeration unit or available, so that one can lower the temperature from this end, that is nearly room temperature, to the liquefaction temperature of hydrogen. But we need to have a refrigerator to produce that kind of temperature. Otherwise, there are other liquefaction cycles, we will talk about it later on, and in that process we will find that we are expanding the gas from here to here, and we follow an isenthalpic line from this point to this point. So, these informations will be necessary. Now, we will now look into the actual TS diagram. You will find this is the liquid vapor dome that we have talked about. This is the liquid vapor dome here, and these are the isenthalpic lines what we have talked about, like this. These are the isenthalpic lines, and also we have talked about the pressure lines or isobars. Say for example, this is what is 1 atmospheric pressure lines, we will see it in details later on. So, 1, 1.5, 2, 3, these are the isobaric lines like this. Say this is what is called about 10 bar isobaric line, and later on this is the triple point, where what we have learned that beyond this part it is not in the liquid form, or this is it will be compressed liquid or near critical region. So, if we follow this line, you will find that this is 1 atmospheric pressure, it is coming over here, and corresponding temperature is nearly 20 Kelvin. So, this graph, this TS diagram is ranging between 14 K to 100 Kelvin, and you see the enthalpy which is having an unit of joules per gram mole. So, here these are the, as we move up you will find that the enthalpy values are increasing, and as we move inside you will find that these enthalpy lines are negative enthalpy lines. So, it is very important to note these values or this unit. Sometime you will find that we are expressing it in terms of the joules per gram mole, sometime it would be in terms of joules per mole also or joules per gram also. So, you have to be careful about the unit. So, this graph or this charts will be supplied to you and you have to read or learn reading this particular chart. So, this is in continuation to the earlier graph which was there from it was here between 14 Kelvin to 100 Kelvin. Now, in this case it is between 80 Kelvin to 300 Kelvin. So, if someone wants you to find out what is the enthalpy at 20 K and 1 bar, say this is the temperature 200 K and 1 atmospheric pressure. So, you have to locate the 1 atmospheric pressure, this is 1 atmospheric pressure how it is going, and this is 200 K temperature. So, there is no line passing through. So, you have to interpolate something like here, say this corresponds to 2700 and on this side you have 2800. So, it is an interpolation, it is a value between 2600 to 2900. This is 2900, this is 2800. Okay. So, we have to interpolate linearly between these 2 points. So, it may be around 2000 what is this is 2700 in between, and it will be say about half of it 2650 or so. But look at the unit, it is you see here this is not in joules per gram mole, rather it is in joules per gram. So, we have to carefully look into its unit when you are choosing these enthalpy values, and when you have to corresponding entropy, if you have to know, you have to come down here and it is say 56, 57, 58, 59, 59, then you have joules per gram per Kelvin. So, that is the unit of the entropy. So, this is how we use this TS diagram for calculating the to find out the enthalpy and the entropy value. Next comes this is in an enlarged version to show it to you that as I was telling that this is the 20 K and the corresponding pressure value is like this. This is for 1 atmosphere, this is for 1.5 atmosphere. So, that means when as you were increasing the pressure from 1 atmosphere to 1.5 to 3 like that, the boiling point is keep on increasing and it will be this is the triple point. So, with the increase in pressure on top of the liquid, you will find that there is the corresponding increase in the boiling point of the liquid, or in other words, if we reduce the pressure on top of the liquid, we will find that it is boiling at a lower temperature. Okay. So, this is about that TS diagram, and say this phase diagram if we want to calculate say imagine that we have some amount of liquid hydrogen given in a container. So, generally they are double walled vessel, this is inner vessel, this is the outer vessel, and we have some amount of liquid hydrogen. So, liquid hydrogen, if it is stored at a particular pressure, if we know the temperature of this liquid, we can determine what is the pressure on top of it, or if we know the pressure on top of it, we can say that what is the amount of liquid, what is the temperature of the liquid, or what is the boiling point at which this liquid is getting stored. So, there this will you will find useful later on while doing the different generation of the solid phases. So, here comes this what we are trying to figure out is this this critical point, and this is the triple point, how this boiling point of the liquid is varying between this point to this point with the pressure. So, this is the relation and there are constants say C1 to C5, and these are given like this. So, once we have these constants and this relation given, we can find out the pressure or the temperature depending on the other. So, for example, if you know that the temperature of this liquid is 15.09 Kelvin, you will find that the corresponding pressure from this relation, if you put all these coefficients, you will find that the corresponding pressure is coming to be how much nearly 14 kPa. So, you can check this value corresponding to 15.09 Kelvin. If we are putting this value over here, then it comes to be 14 kPa. So, here this P 0 is 101.3 kPa, that is the atmospheric pressure. So, this is P 0 and T 0 is the corresponding boiling point. So, that we have learned to be 20.3 Kelvin. So, if you apply these values in this equation, you will find the corresponding pressure comes to be P 0. So, this is about the phase diagram which we will use to determine the different phases in the coming lectures. So, now let us conclude and let us before that we will have the references. So, the same references we have given in the earlier lecture. So, there is no more additional references, you can go through this. And in conclusion, we have learned that the normal boiling point of liquid hydrogen is 20.3. Then we have learned the critical temperature, then the critical pressure, and the triple point temperature and the triple point pressure. So, thank you for your attention.